There is no air in space, so when a rocket turns, what exactly is it pushing against? Rockets don't use wings, steering wheels, or air, yet they can turn with terrifying precision. Here's how. One wrong move in space doesn't crash a rocket, it sends it drifting forever. So how do rockets stay on course? Most people imagine rockets steering the same way airplanes do, by using wings and air pressure. That idea makes sense on Earth, but in space it completely falls apart. Rockets don't need air to steer. They don't rely on wind, drag, or lift. In fact, rockets are designed to work where air doesn't exist at all. So if there's nothing to push against in space, what exactly allows a rocket to turn, rotate, and stay under control? The answer begins with one of the most important rules in all of science, a rule so powerful that it governs every rocket ever launched, from the earliest space missions to today's reusable rockets and future Mars explorers. This rule is Newton's third law of motion. For every action, there is an equal and opposite reaction. This single principle explains not only how rockets move forward, but also how they steer, stabilize, and survive in the vast emptiness of space. So how do rockets actually steer in space? Instead of pushing against air, rockets push against their own exhaust. When a rocket engine fires, it throws extremely hot gas out of the nozzle at incredible speed. That gas rushing in one direction forces the rocket to move in the opposite direction. Change the direction of the exhaust, and you change the direction of the rocket. Steering, at its core, is simply controlled force. During launch, this steering happens inside the rocket's main engines. The engine nozzles are not fixed in place. They can tilt slightly, a technique known as gimbaling. Even a tiny adjustment, sometimes less than a single degree, can alter the rocket's entire trajectory. A small tilt near Earth can mean the difference between reaching orbit or missing it by thousands of kilometers. Legendary rockets like NASA's Saturn V used this system, and modern rockets like SpaceX's Falcon 9 rely on it every day. But rockets don't stop steering once the main engines shut down. In many ways, steering becomes even more critical after reaching space. Without strong gravity pulling in a single direction, and without air to naturally stabilize motion, a spacecraft can begin to spin, drift, or rotate uncontrollably from even the smallest disturbance. To stay on course, the spacecraft must constantly make tiny corrections. This is where reaction control systems come into play. Small but powerful thrusters positioned around a spacecraft fire short, carefully controlled bursts of gas to rotate the spacecraft, change its orientation, or keep it perfectly stable in the weightless environment of space. Unlike main rocket engines, RCS produces no loud roar and no dramatic flames. The movements are silent, subtle, and extremely precise. Using this system, a spacecraft can turn itself around, point antennas back toward Earth, align its solar panels with the sun for power, slow its rotation, or prepare for delicate maneuvers like docking with a space station. So who is actually controlling all this steering? Surprisingly, it's not humans, at least not in real time. While astronauts and engineers carefully plan the mission on Earth, the moment a rocket leaves the ground, control shifts to onboard computers. These systems constantly read data from sensors thousands of times every second, tracking speed, rotation, and direction with extreme precision. The instant even the smallest unwanted movement is detected, the computer responds by firing engines or thrusters to correct the course. Humans decide where the rocket needs to go, but in space, computers do the driving. Where does steering matter the most? It matters during the most dangerous and critical moments of any space mission. During stage separation, even a tiny error can cause collision. During orbit insertion, incorrect steering can send a spacecraft drifting endlessly into space. During docking with the International Space Station, precision must be perfect because both objects are moving at incredible speed. During planet landings, steering can mean the difference between a historic success and total loss. When steering fails, the consequences in space are severe and often permanent.
Unlike on Earth, mistakes don't fall down, crash nearby, or offer a second chance. In space, errors drift endlessly into the void. A satellite with faulty steering can begin spinning uncontrollably, unable to point its antennas, orient its solar panels, or communicate with Earth. Power fades, signals vanish, and the mission quietly dies. A spacecraft that misses a critical maneuver by even a fraction of a second may never recover its trajectory, slipping past its destination and becoming lost forever. There are no repair crews, no tow trucks, no emergency landings. Every movement must be perfect. This is why steering systems are among the most rigorously tested components in aerospace engineering. They endure thousands of simulations, extreme stress tests, redundant architectures, and multiple backup controls. Long before a rocket ever leaves the ground, engineers assume failure and design systems that refuse to let it happen. Why does all of this matter to you? Because modern life depends on rockets steering correctly in space. GPS navigation, weather forecasts, satellite internet, global communications, Earth observation, and future exploration missions all rely on precise control in a place where nothing is forgiving. Every successful rocket launch is not just a blast of power, but a careful dance with physics. So the next time you watch a rocket rise into the sky, remember this: it's not just fighting gravity, it's using invisible forces guided by math, physics, and computers to navigate through pure emptiness. With no air, no roads, and no second chances, rockets steer by mastering the laws of nature.